Welcome to AP Chemistry. Most of what you need to know in terms of information for the AP test and for this course will be presented in this series of videos. This is your first video, Unit 1, Learning Goal 1. Our learning goals are really just a list of concepts that you need to know for the test. At the end of every unit, we'll use our study guides for the unit as a list of learning goals to review. And at the end of the course, we'll use all of our study guides for all of our units to review for the AP test. This first learning goal is about dimensional analysis and the mole concept. And you're a student of chemistry, so you've seen this before. But let's review what is dimensional analysis and what is a mole. So what is dimensional analysis? It is this concept that we can take a measurement, something that we can directly record and visualize, like the mass of a substance or the volume of a substance, and convert it into information that is useful for calculating ratios and proportions of molecules and atoms, which are things that we cannot directly visualize. Atoms and molecules are way too small for us to see and count. So we take information that we can measure and convert it to information that we can't. And the way that we do this is by the use of conversion factors, things that we have worked out to be equal to each other. And when you have two things that are equal to each other, kind of like 12 inches is 1 foot, right? And when you take those things and you make them a proportion, you've got two things that are equal to each other that are being divided, and anything divided by itself is 1. So if you multiply, that's the factor part of the conversion, if you multiply by this conversion factor, you're really multiplying by 1, which doesn't change the essence of the measurement that you've made. All it does is convert the units that you're measuring that thing in. The most common use of conversion factors for chemistry is to convert to this unit called the mole. The mole is an understanding of, it's a kind of like a dozen or a gross or something like that. It's a common number of particles and molecules that can now be equated in ratios. So molar ratios are proportions to molecular ratios. It's just a huge number of atoms and molecules so that we don't have to calculate things at this atom and molecule level, which is like a really huge number of atoms and molecules that we would have to work with. So it's kind of like taking those 12 inches and making them a foot, or maybe when we want to measure really huge distances, now we measure in miles. So the mole is kind of like taking that inch, or actually maybe a fraction of an inch, and making it a mile, just so that it's more practical to measure, right? If I was measuring from here to France, I would not want to measure in inches. That would be ridiculous. And that's the same kind of idea that we have with molecules. If I'm doing a reaction, I don't want to count number of molecules. It's a ridiculously huge number. So I use this concept of the mole to take those molecules and put them into a package of a huge number of molecules, but all of those packages are the same number. So how do we do that? Well, we use ratios and proportions, and our understanding of the mass of each atom, take that mass, make a really big number of those things, and change that to grams. So it's actually pretty simple to use moles. What we do is find the mass of the substance on the periodic table. That mass is the measured mass in atomic mass units for one atom of that substance. But that mass in grams is the mass of 1 mole of that substance. And if we need to do that for a molecule, we just add up all of the masses of the individual atoms, and that becomes the molar mass of the molecule. So, to sum up, the mole concept is a way of converting from something that I can measure, grams or mass, and then converting that to these packages of molecules, always the same number of molecules. And I just do that by using the mass on the periodic table. Now, the number of molecules in a mole is also something that you'll want to know. It is a number you don't have to memorize, but you probably will, 6.02 times 10 to the 23rd. That number is found on the AP Chemistry list of equations and tables that you're allowed to use for the test. But it's got a special name. It's one that most chemistry students do memorize by heart. 6.02 times 10 to the 23rd is called Avogadro's number. Avogadro was not the person who actually discovered this number, but they named it for him because he was one of the pioneers in really defining this mole concept, that we can take something that we can measure and say that equal volumes of a gas are equal number of molecules. And that was Avogadro's original idea, was to convert volume of gas to number of molecules. Later, after this was more developed and this number was discovered, they decided to name the number after Avogadro because he was such a pioneer in this molar concept. This won't be used a lot when we convert things for reactions. It is used more when we start talking about energy and numbers of electrons that are transferred in reactions and so forth. But the mole ratio of two chemicals in a reaction is often used to convert from one type of chemical to another chemical in the reaction. It's often used as kind of the pivot point of dimensional analysis when we're converting from information that we know to information that we want to know. Other ratios and proportions might be used in dimensional analysis as well, such as the concentration of solutions, converting from the volume of solutions to the mass, or to the moles of a solution. And then also density, converting from the volume of a liquid to the mass of a liquid. So ratios and proportions are already set up as conversion factors because they compare two units to each other. For example, concentration is moles per liter. We've got 2 units already in that ratio, so it can be used as that conversion factor. Conversion factors can also be used in either reciprocal form, because it's something divided by itself is 1. And so we can flip that over as we need to in order to cancel units that we know and convert to units that we want. Let's get this information into your study guide. And so you can pause the video and copy it into your study guide. And then we'll practice some AP problems that relate to dimensional analysis and the mole concept. And we'll call this learning goal done at that point. So go ahead and pause the video, put this in your study guide.
Now we're going to do some AP examples that have to do with dimensional analysis and the mole concept. Here's your first one. Pause the video, try the problem, and when you're ready, push play to see the answer. The question mentions Avogadro's number, which we know is used to convert from moles to particles, which could be molecules or atoms. In this case, molecules is being asked about. How do we get to moles? Well, we know we could get there from grams if we know the molar mass, which is a choice in 2 of these selections. To get from grams to moles, however, we need to know how many grams we're starting with, which is the mass of the sample. The correct answer for this problem is C. Here's a second example. Pause the video again, try this problem, and when you're all done, push play. This question is asking about oxygen. When we find it on the periodic table, we see that oxygen has a molar mass of about 16. So let's do some dimensional analysis, starting with a 1 gram sample of our first sample of Na2O. We start with the 1 gram, and we use our mole mass to convert from grams to moles. And then we're going to use the compound itself, sodium oxide, and say that for every 1 mole of sodium oxide, we would have 1 mole of oxygen, because there's 1 oxygen in the formula. Lastly, we convert from moles of oxygen to grams of oxygen, and without putting this into the calculator, what we can see is the fraction will be 16 out of 62. The rest of these compounds should have similar dimensional analysis, and so what we can see is we're looking at the mass of oxygen divided by the molar mass. We can't use a calculator on the AP test for this part of the test, the multiple choice. So this is the best that we can do. And if we look at choice B, we're dividing by the smallest number, and that should give us the largest number overall. Let's do one more example. Pause the video, and when you're done solving this problem, push play to see how you did. This question is asking about a mole fraction. So we need to know that a mole fraction is the mole of the substance we're concerned with, in this case methanol, out of the total moles in the solution. And that would make a mole fraction. So we need to do some dimensional analysis because we're given grams of these substances and we need to convert those into moles. So let's start with the 128 grams of methanol, and we convert that into moles of methanol, CH3OH, by calculating first the molar mass of this molecule. So 1 mole of CH3OH would be 12 for the carbon, 4 for the hydrogen, and 16 for the oxygen. That gives us a total of 32 grams. 128 divided by 32, I can do in my head, that is 4 moles of methanol. So then we move on to the water, 108 grams of water. The molar mass of water is 18 grams per mole, 16 for oxygen and 2 for hydrogen. 108 divided by 18 is 6. Nice even round numbers because we're not allowed to use a calculator on the multiple choice section. So altogether the mole fraction is 4 methanol out of 10 total, and that's 4/10. That's it for this video. You're ready to move on to the next one. Good job.